All right, welcome back. This is the third video of the sixth lecture of the engineering design course. This is the slide that we stopped on last time, but I had completed talking about it, so ready to move on to the next one. This is just really a synopsis of the function analysis method and then a description of a couple of kind of neat ideation opportunities. How do you know when you've got the right combination of subfunctions connected to all of the flows of energy, information, and material through the system? How do you know that configuration is correct? Well, one of the things to check is first to make sure that all the inputs and the outputs either connect to a subfunction, and of course, as we saw in the previous example, the subfunctions either conduit the energy, information, and material through them, or they somehow transform energy, information, material. They can combine them, they can separate them, but they act on those flows through the system boundary. But all inputs and outputs must either connect to a subfunction, or if they don't connect, they have to exit the product boundary. And the reason that they have to exit the product boundary is any unconnected flow of material or information or energy that is left inside the system boundary is essentially an accumulation, right? So if you've got material flowing into the system boundary that isn't somehow manipulated by a subfunction and does not flow out of the system boundary, well, that material is just going to accumulate inside the system boundary, and that does not make any sense from a mass conservation perspective. So make sure that all your inputs and outputs either connect to a subfunction or exit the boundary. The second aspect is that the set of subfunctions that you choose to contain within the system boundary essentially define the product. And it's this aspect of the function analysis method that I most like, in addition to it being kind of an offshoot of the system boundary method and that we learn in thermodynamics, and the block diagram method that we learn in controls. It also allows you to essentially decide what the product does and what the product doesn't do by setting the boundary around the subfunctions that you're interested in. And those subfunctions, of course, should meet the client needs in the customer needs statement. But as you'll see in a moment, there's some neat creative ideation opportunities that come from manipulating the system boundary. So it is possible to redraw boundaries to include or exclude different subfunctions. And in doing so, you're essentially describing different products. So remember in the beginning, the first slide, we talked about the need to define the scope of the design space, whether you're designing just a simple handset or whether you're designing an entire enormous telecommunication system. Remember that example? The doorknob was the other one where you could actually come up with a way to get into and out of a building without a doorknob. So that's a much larger space, much larger design space than the doorknob by itself. Or you could just accomplish the same thing with a simple latch, which is a much smaller design space. So anyway, here is the mechanism by which you can change the size of the design space by either incorporating or excluding different subfunctions. And I'm going to show you an example of how to do this here in a second. But in addition to being able to control the design space and set the appropriate design space size for your particular problem, this is also an ideation opportunity. So it actually can be helpful if you want to do some creative ideation to intentionally include or exclude functions and imagine how to design a viable product that either includes those strange functions that you should have excluded, or that excludes what you think are critical functions that you feel like you want to include, and you can come up with some really creative solutions that way. The final thing that you want to do, the final thing that comes out of the function analysis method, is the beginning of thinking about prototyping, and that is now that you've identified the set of sub-functions that make up your product, you can then start to identify suitable components, either commercially available components or components that you can build yourself that meet each of those sub-function requirements and essentially do what the noun-verb combination that you set for the subfunction says that the subfunction can do. And what's great about living in the 21st century is that there are a variety of different components that one can select that all essentially do similar functions. So it used to be that just about everything that you wanted to do, you had to have a mechanical solution for. And now there are a lot of very sophisticated electronics components that replace a lot of the older mechanical components that we used to use, say, 20 or 30 years ago. So sit and think for a moment about each of the sub-functions that you contain within your system boundary and what component or what device or what object you would buy or build that would do those things. And it's good to think about electronic components, mechanical components, even textile components. Surprisingly, textiles are incredibly versatile and serve a whole lot of different sub-function requirements. And people don't really think about textiles, but they're in a whole lot of things. So for ideation purposes as well, thinking of all these different possible combinations can be quite helpful to coming up with new ways to solve your design problems. Okay, I do want to give you guys one example of how to change system boundaries and how that changes the outcome, the design solution. But I'm almost up to 7 minutes here, so I'm going to take a quick pause on this slide, and we'll come back and do a final video after you guys take a quick break. So see you in just a moment.